Hi, today I'll be talking about polymorphism in Java. Polymorphism is the ability to process multiple types as one in the code. So you can write a code to process one type, one class of objects at compile time, and then at runtime you can execute different types of objects. Not only that, each object executes its own behavior. The behavior defined in its own class. The objects that you can do this with are instances of classes that are descendants of a common ancestor. They all inherit from the same ancestor. That's how you know them in the code. That's how you refer to them, by that ancestor. That ancestor can be a superclass, a superclass, any class that is higher up in the inheritance hierarchy. It can be an abstract class, a concrete class, or an interface. The fact of the matter is they all have the same ancestor, which we use to refer to them all. The process here, that behavior that is taking place, the method, is known to them all also. It's defined on that common ancestor, so all the descendants have that method also. They are inheriting from it. In the end, you're coding to process objects of that ancestor type without having to know which descendant objects will be coming in at runtime. This all happens in an inheritance hierarchy. We've been talking inheritance here all along. Polymorphism takes place in a structure laid out by an inheritance hierarchy. There's no such thing as polymorphism without inheritance. And polymorphism applies only to methods. There's no polymorphic behavior in fields. Polymorphism is possible by two things, two features of Java language. One is a superclass pointer can point to any descendant object in the code. Here we have, for instance, a variable of type object, the class object. We are using it to refer to an instance of linked list class. This is perfectly fine because object is a superclass of linked list. Linked list is inheriting from it. It's in the inheritance hierarchy branching down from class object. In fact, object is the ancestor of all the classes there are, and there can be in Java. So we can do this. We can also do this with an interface or an abstract class. We could have, for instance, declared this variable as a collection or an abstract list or an abstract collection. They all are supertypes of linked lists, so they can all point to a linked list object. By the way, we are using generics here. The linked lists and all of them, all the collections are parameterized, but we don't need to know about generics. We won't get into that in this video. It's a whole different topic. Polymorphism has a lot to do with, or rather, generics has a lot to do with polymorphism, but we won't get into that. And you'll be able to follow this video without having to know generics. The second thing that makes polymorphism is when we invoke a method on an object, the method that is executed at runtime is the overridden version of it on the class of the object itself, not the one on the class of the pointer referring to it. So here in this line, For instance, we are calling upon the toString method of the object we have at hand. We can do this. toString is one of the methods defined in the class, so it's perfectly fine here. The println method here will invoke toString at runtime. That's what it does. It invokes the toStrings of the objects it's printing and prints the values they return. So when it's time to execute this line, the method that is executed at runtime, the toString that is executed at runtime, is the one on linked list, not the one on object, class object. Java runs linked list's own version of toString here. It goes by the instance type, not the pointer type for method invocation. Now, the toString of linked list can be an inherited one, and it is. Linked list isn't overriding toString itself. It is happy with the one it's inheriting, and that's from abstract collection, the nearest ancestor that has it. But it is its own toString method, and that's the one that runs at runtime. These two are the things that make polymorphism. This is what it boils down to. Now, this second feature here is the difference between field members and method members when it comes to polymorphism. It only applies to methods, not to fields. Remember, we said earlier that polymorphism exists only in methods and not fields. This is where they go their own ways. For fields, the pointer type is the one that tells which field definition, not the other way around, not the instance type. This is why fields don't have polymorphic behavior. Now, we won't go into that in this video, but just a quick note, the term for this is hiding. When you define a field with the same name and type as a superclass field, you're hiding it, not overriding it. Overriding is a polymorphism term. Methods are overridden, fields are hidden. Now we'll look at all these in the code. We'll see them all in the flesh. We have a linked list object again, parameterized again. Collections that are never meaningful as row types. It's declared as an object again. We'll see what it prints. But before that, let's see what object and linked list themselves print, what each print here. Let's take a look at them. So here we go. This is what object printed. So in these statements we invoked here. We might just as well have coded them like this. Oh, toString. Here we go. So the first is the object. This is what the toString of object, class object, is printing. Let's see these in the code. Here we go. Here we go. So this is the object toString of object class. This is the method running in this first line here. This is the first line, the second line. This is the method running. The toString of object. It's an object. It's an instance of class object, so it just invoked the method on it. And for the second one here, it's printing the entries in the list at the time as a comma separated list. We didn't put anything into the list. We're not seeing anything here. But this method, the one on abstract collection, is the one that has been invoked when this line executed at runtime. When it came to execute this line at runtime, Java looked at the class linked list itself. Java saw that this method is invoked on a linked list object, so it went to the linked list class to look for a toString method, but there isn't anything there. It couldn't find an implementation there. Linked list is not overriding toString itself. It's happy with the toString it's inheriting, so it doesn't override. So not being able to find it on linked list, Java went one level up to look for it there. Not there either. Abstract sequential list doesn't have a toString method either. Then one level up, always one level up, bottom up. Abstract list doesn't have that either, and so Java went to, at runtime, went to abstract collection to look for the method and found it there and stopped there, ran it, which produced this string. Now let's look at the other instance, the one we here declared. So here we declared, we have a linked list object again, declared as an object. Let's see what it prints. So it's the toString of the linked list. At runtime, at runtime, it invoked the toString of the linked list itself. Now, toString method of linked list happens to be an inherited one, and it always inherits from the nearest ancestor, but its own toString. Java didn't say, oh, this is an object instance. It is a linked list instance, but it's declared as an object, so I use the toString of the class object. No, at runtime, Java always goes by the object when it comes to method invocation. The type of the reference variable here is only for compile time. It has no effect at all at runtime. Now let's take a closer look at this assignment statement. There's some more happening here than there is in here. Here, for instance, we are also using a linked list, but directly without a reference to it. So this is an assignment statement. A value is being assigned to a variable. First of all, Java is a statically typed language. The types are checked, verified at compile time to see whether they match. If they don't match, a checked error, compile time error is given, and it doesn't compile. We can't get to the runtime. The bytecodes don't generate. So at compile time, what happens is Java looks at the type of the value here. It's a linked list. And then it looks at the type of the variable declared, or the variable we are assigning it to. Our variable is of type object. Do these two match? Yes, they do. Object is a supertype of linked list. Linked list is inheriting from object implicitly. It's extending of, so everything is fine. The types do match. There's one more thing happening here. Linked list, this linked list instance is upcast to this type, to the type of the variable. This is also happening implicitly. This means from this point on, whenever we refer to this object by using this reference, this pointer, this variable, it will be seen as an object at compile time, not as a linked list at compile time. Just because we told Java to do so, we declared it as an object. Now let's add some entries and see them printed here. Linked list has an add method here. Let's use it. It's an integer list. Let's add 5, for instance, an integer. Now this didn't compile. This is a checked error. It won't run. It will give a, yes, it threw an error exception for us. Just because we told Java to treat it as an object, not a linked list. So we have to downcast it this time. Cast to its type, or a type where we can do this. Let's go for it for its own type. Here we go. Let's add some more, a few of them, and another. Yes. Here we cast it to its, downcast it to linked list, back to linked list again, and then invoked the method on the object. We could have done this in an assignment statement. Let's say list and then invoke the method. Let's add 99. Here we go. This time we explicitly, this is an explicit typecasting. We cast it to linked list or a type. We could have done this to a superclass. Superclass list is a superclass of linked list. It's a supertype, and the method add is defined on the list, so that would also work. So we did the casting explicitly. Downcasts are always explicit. We cast it in an assignment statement and then used it. The interesting thing here is it's the very same object at runtime. One linked list instance here is sitting at one specific memory location. Both this variable and this variable are referring to the same address, its address, but this is seeing it as an object and this as a linked list. In the end, whatever we did worked on that one specific, one and the same object. Suppose we are given this as a task. We are asked to print objects at runtime, whatever their toString methods might be saying. This is the method that does that. It prints the objects passed to it here in these two lines. Let's run it. Here we have several objects of different types. These are the ones with the braces are the collection objects. This is the date. It's printing its own way. It's printing the date with a certain format, and this is the thread instance, and so forth. This is polymorphism in action. We coded to process one type. The type object is just this one line here. And we executed multiple types. We've been able to do this because we can use a superclass pointer to refer to any descendant object at compile time. But that doesn't stop each object from running their own behavior, own method at runtime. Here, for instance, all these different toString method invocations are executed by this one line. Date ran its own version of toString, thread ran its own, linked list its own, and so forth. We didn't have to be specific with each type. We didn't even have to know which types will be coming in at runtime, as long as they are subtypes. This is polymorphism. This is what it is about. It uses an inheritance hierarchy to do these. Inheritance is a structural aspect of the object-oriented paradigm. Polymorphism is behavioral. It puts a common behavior defined in an inheritance hierarchy at an effective use. This is what it exists for. This is the essence of polymorphism. Suppose now we are asked to tell the number of linked lists among the objects given to us. This is the code to do that. We are using the getClass method to make this happen. What it does is, let's run this. So we invoke the method with two linked lists among the parameters, which is what it's telling here. getClass is one of the methods in class object. It tells the class the object is born to. Every object comes to life as an instance of a concrete class. For instance, the date here, date object, it is born as a date object. It won't be anything else ever. It will live as a date object and die as a date object. As long as it sits in the memory, its type will be date and date only. Nothing will ever change that. This here is a linked list. It will always be a linked list as long as it lives, no matter what type of pointer we are using to refer to it. getClass is the method that tells this for each object, the class it belongs to. That's its job. That's what it tells, and it doesn't tell anything else. It's a final method. It can't be overridden, so it doesn't tell anything else even if you wanted it to. So in our code here, we are using getClass to see whether the object at hand is a linked list, and if so, incrementing our counter to get what we want. Let's now assume that we are asked to deliver the total number of entries in all the collections there are among these objects. This is the code to do that. Let's run and see it. For example, in this call, the total count is 5. We put 5 entries to this linked list here, and it is one of the parameters in this call. There are other collections we are passing in. This hash set, stack are also collections each, and we are passing one other linked list, but they don't have any entries in them, so the total count is 5. For this, we are using the size method. There's a size method in the collection hierarchy. It's defined on the collection interface. It tells the number of entries in the collection object. Size is not defined on the class object, so we are downcasting to collection here and then calling size on it. But even before that, even before downcasting, we are looking to see whether the object at hand is indeed a collection, because otherwise we get a class cast exception, a runtime exception. Let's see this happen. Let's comment out the type checking here and see what happens. Here we go. The first two parameters of the call are collections. The two linked lists here, they are processed fine, but it threw a class cast exception when it came to the date object. The types didn't match. It attempted to cast the collection, but date is not a collection. That's an error. That's the exception thrown here. So we are first making sure that the types are right, that we can cast this object to this type. In other words, the object here is an instance of type that inherits from collection. We are using instanceof here to do that. It takes a class type on the right hand side and an object on the left hand side and tells whether the object is of type that is a descendant of the class on the right, whether it inherits from that class or is the class itself. It's pretty much the wording here. It tells whether the object is an instance of collection, whether it is in the inheritance hierarchy branching down from collection. So this expression here will return true only if the object at hand is a collection, like stack, linked list, tree set, etc. If it isn't, it will return false and won't execute the if statement body, which is what we want. Before we finish, let's take a look at the difference between getClass and instanceof. They sound similar, but they aren't. First of all, getClass is a method and instanceof is an operator. It's a binary operator that returns true or false. But more interestingly, getClass has nothing to do with inheritance. Instanceof has everything to do with inheritance. getClass merely returns the class type of the object. It doesn't look at the inheritance relationships the class might be in with other classes. Instanceof, on the other hand, tells the inheritance relationship between its two operands. It tells whether the left-hand side type is a subtype of right-hand side. That's why it exists. That's its reason for being.